Hello, further mathematicians. I'm just going to be here finishing off the last little bit of the Matrices chapter 6 um, before we move on to chapter 7 next week. So, I'm going to be talking about consistency of linear equations. A few people have emailed me and asked about this, so I think it is good to get a bit of a video out there about it, maybe me explaining a few things, and you can message me on Teams of any further questions you might have. So, I'm going to talk about consistency. So consistency talks about the number of and the nature of solutions to a set of linear equations. Okay, which is known as a linear system. So these are two equation systems. I think we are probably aware at this point we can write them as matrices, as I have done below here, and we can think about, are these consistent, i.e. do they have solutions, and what is the nature of their consistency or their lack of consistency that they have. So this is a nice one. The determinant here is non-zero. You can check that in your calculator, but I'm going to say determinant is not zero. So it's not a singular matrix, which just means it has a solution. A single solution exists. So a single solution exists. In this case, the second set of equations here, again, I think it's fairly clear what's happening if we look at this. You can see immediately the determinant here is 0. So the determinant is 0. Because these rows in the matrix are the same. So if I do this times this and I subtract them, that's going to give me nothing. So this determinant here is 0. We just need to think carefully about what that means for our set of equations. So we just need to think, what happens if I draw these equations? You can see what's going to happen just by looking at them. But if I go here, I've drawn these two equations, so x minus 3y equals 1, x minus 3y equals 2, and it's pretty straightforward. They're just parallel lines, and you can see they're parallel lines from looking at them. Okay, so it's a pair of parallel lines, which means there is no solution. So this is not consistent. Whereas this one, I should have said, this is consistent. So now let's have a look at this last pair. So again, you can see straight away that the determinant here is 0 because these two rows are multiples of each other. This is twice this. And again, we can just calculate it to check it. It's very easy to do. But now we need to think, how is this different to the previous example that I just looked at? In this case, these lines look like they're parallel, but there's something else much more interesting going on here. Not even, well, depends what you consider interesting. But if I get rid of this one, so now I've got this line instead. These are the same line. They are literally complete multiples of each other, including the constant value on the right hand side of the equation. So the fact that these are complete multiples of each other means that they are in fact the same line. So both the same line. That does actually mean that yes, they are consistent, and it also means that there is an infinite number of solutions. Who the hell is... That's not my Facebook, I'm not on Facebook. There is an infinite number of solutions. It's infinite because if we look at this line and then we just think about what is going on this line, well, both the lines are on top of each other, which means that every single point is where they intersect. So every single point on this line in both directions to infinity is in fact a solution. So there's infinite solutions. Okay, so we're going to have a look at 3D systems now. So this is talking about planes. So if you have an equation like this, 3x plus 2y minus z, so an equation with three variables in it, it's not going to plot a straight line through 3D space, it's going to actually plot a flat surface. So that's some examples like this. So these are kind of 3D flat surfaces floating in space, but we would still draw them in a nice coordinate system like this one, like the classic 3D coordinate system that we use. But there's just going to be a nice flat surface going in all directions to infinity, unless of course we have a domain for it. Represented by these equations. So let's just get rid of that. So there's a bunch of possible scenarios here if we have a set of 3 equations, and they can be quite hard to spot. So I've kind of labelled these planes with colour because I didn't colour them all in, because I just stole this random picture off the internet because I couldn't work out how to draw some planes myself. So 3 parallel planes is the first case I've got here. I've labelled this number 1. 3 parallel planes. So if 3 planes are parallel, then they cannot be consistent because they don't intersect anywhere. So there's no solutions. We actually have a similar scenario going on here, although you might not find this quite so obvious to think about. If in this case, number 2, there are 2 parallel planes. Planes. There are 2 parallel planes. So red and green, in this case, the red and green plane are parallel to each other, and the blue one intersects both of them. So that might lead you to think that these 2 lines could be considered to be like a set of solutions, because that's where they intersect. But the important thing is that the points on these lines, if we say they are a solution, they have to be a solution to all 3 equations. So the equation for the green, the red, and the blue plane, it must satisfy every single one. So any point where the red and blue plane intersect isn't going to be a solution to the green plane, because they're parallel, so they can never intersect. So again, if there's only 2 parallel planes, they are still not consistent, and they're also got no solutions. Scenario 3. So scenario 3 is where all 3 planes meet on the same line. So you can see they've kind of not Constantine, I don't even know what the correct word is for this, but I do know what the correct word is. It's called a sheaf, but I just cannot think of a more practical word to use to explain it. This is called a sheaf. They all meet in the same line. So this line, the green line that I've highlighted here, is where all 3 planes go through. So they meet on a straight line, all 3 planes in the same place. So this means they are consistent, and there's infinite solutions, because any point on that straight line is going to be a solution, just like when we had the 2 lines that were on top of each other in the other example. Oh, sorry, my hands get a bit tired from writing this pen. So number 4 is quite an interesting situation. It's when they aren't parallel and they don't meet on the same line. They're all just kind of floating around randomly in space. And if that's the case, what's going to happen is we're going to get this, where these planes are going to form a triangular prism. So this is the triangular prism case. So if they form a triangular prism, again, it's kind of like this situation. There's 3 lines they meet on, but on none of these lines, like if I said, okay, well let's highlight this line red. Come on, pen, work properly. So if I highlight this line red here, you might think, well, these are solutions to these 2 planes, but it's this plane at the bottom, nothing on that red line is a solution to this plane. So this actually would not count as a solution. It's just like in the other case as well. So it's triangular prism, and again there's no solutions here. So because there's no solutions, we again say it's not consistent. Finally, the easy case. The easy case is when we have this here, which I'm going to do it in different, not going to do it in red because that might think it's not a solution. So if we have they meet at a point like this, the one point here, so you can imagine like if it was a 3 planes forming 3 sides of a cube, the corner of the cube would be like a point where they all meet. So it's a bit like that kind of situation. Meet at one point. Meet at one point equals consistent. Is consistent. Consistent. And there's one solution. There's one coordinate in space that exists as a solution to this. So it's important to note, if I think about these 4 cases that I've just put a box around here, if we represent these sets of equations as being a matrix, this would have determinant 0. These would all have a determinant of 0. So all matrices that would represent sets of equations organized like this, even for number 3, which does have solutions, infinite solutions, would give you a determinant of 0. So if you've got a non-zero determinant for your matrix, you can really easily see, well, it's invertible, so it must have one set of solutions. But if we have a case like this one, or any of these 4, we have to investigate it a bit more carefully, because if it's a scenario 1, 2 or 4, then there will be non-consistency and no solutions. But if it's got a 0 determinant and we can show that there's a line where points will lie along for all 3 planes, then, well, that means that it is consistent and there's infinite solutions. Okay, returning to this. So looking at these simultaneous equations that we have here, solve if possible, sure, and state the nature of the set of planes represented. So I'm not actually going to solve them because you know how to solve them. You write them out like this, and then you multiply by the inverse. Really what we need to do is think, does the inverse exist, i.e. is the determinant 0 or not? And then if it is 0, does it have a set of solutions or not? So in this case here, I've put this in my calculator already. The determinant of this is 0. It's not 0, it's minus 20. So I'm just going to show you that here. Just a quick reminder, how do you find a determinant? Scroll down, determinant, and then I've labelled this B to be matrix A. So there we go. Determinant of A is minus 20. So yeah, it's consistent. And it has a single solution. I'm not going to bother doing that though, because you should know how to do it. Right, so let's have a look at question 2 here, using a similar idea. So looking at this second question here, which I've written out, I've put the matrix in my calculator again. I kind of slightly naughtily also called this one A. I should really have given it a different name, but it's too late now. So here, the determinant of this matrix is 0. So just to show you again, option, determinant of matrix A, find it out, it's nothing, 0. So what we have to do now is we have to think, what situation here, 1, 2, 3 or 4, do we have? Because if it's 1, 2 or 4, this is non-consistent, but if it's 3, what we have is an infinite set. Oh, Jesus, we have an infinite set of possible solutions. So I think first of all, it's easiest to eliminate 1 and 2, or say if it is 1 or 2, because if it's 1 or 2, so in the case of 1, all 3 equations would be multiples of each other, but they would have different like non-multiple constants on the right hand side. So if that was the case, it would be quite easy to spot that, and it's clearly not the case, and you can see it even more so because there's no x here. I mean, it's just obviously not the case that these are multiples and they're not parallel. So we now need to ask ourselves, because none of these equations are parallel, so either 3 of them or 2 of them for situation 2 would have to be parallel. It's either going to be 3 or 4. So for 3, we need to show that they're a sheaf, or for 4, we need to show that they are not a sheaf. And that's a similar process for both of these situations. So what I'm going to do is I'm going to look at this set of equations that I have here, and I'm going to just manipulate them and do a little bit of algebra. So I actually have an equation just in y and z at the bottom, and what you want to do if you're testing this, if they're not parallel obviously, and you're trying to think, well, okay, is it a prism or is it a sheaf? What we want to do is eliminate a certain variable. So here x is already eliminated, so I could just use this first pair of equations to eliminate x as well. So if I do 1 minus 2, x minus x is nothing, 2y minus y is y, 3z minus z is 2z. Should spot what's happening here. 3 minus 2 is 1. And that equals equation 3. This is equal to equation 3, if I label this one 3. So the solution of these two equations is this equation. So it's kind of simple to imagine that what that actually means is that if the solution to these two equations is this line, then they all meet on a single line, because this equation and these two equations can all be reduced to the same line. So we want to eliminate a variable like x in this case. So these solutions mean that yes, it's consistent, and there is an infinite amount of solutions. Infinite, if I spelled that right, I don't know. Infinite solutions. Infinite number of solutions, I should say. Okay, and that's going to be on this line, y plus 2z equals 1. So let's have a look at number 3 then. Let's have a see what we think about this. Alright, so I've drawn out this set of equations as a matrix, and what I am, where am I going? There we go. What I am going to do is I'm going to again think, well, first of all, what's the determinant? The determinant is 0. It's important to note as well, if we look at both of the examples I have just done, it's not immediately obvious that the determinant is 0 using the check if it's a multiple method. So it's not always the case. So you do have to put it in your calculator and kind of think about it a little bit. So I'm going to do the same thing again that I did with this second question, and I'm going to eliminate the variable x. I'm just going to pick a variable to eliminate. It's going to be easiest to eliminate x here and form a pair of equations that are not involving x. So what I'm going to do is I'm going to say this is equation 1, this is equation 2, this is equation 3. So my goal is to form a set of linear equations in 2 variables. So like I did here, y plus 2z, I made 2 equations in y and z. I'm going to form a pair of simultaneous equations in 2 variables using the equations that I have in 3 variables. You should hopefully spot if I do 3 minus 2 lots of 2, and if I do 3 minus 2 lots of 1, 3 minus 2 lots of 2 would eliminate the x's, and 3 minus 2 lots of 1 would eliminate the x's, and that would leave me with 2 equations that were just in terms of y and z. So 3 minus 2 lots of, I've written 2 first, haven't I? So 3 minus 2 lots of 2. I'm going to do 2x minus 2x is nothing, minus 7y, take away, minus 3 times 2y is actually minus 1y, and then 8 minus 2 times 3 is 2z, and that is going to be 4 minus 2 times 3, which is minus 2. 3 minus 2 times 1, so again the x's go to 0. Minus 7 take away minus 4 is minus 3. Minus 3y. 8z take away 2z, it's going to be 6z. So we can already see actually this and this, the y's and the z's are 3 times each other. But if I do 4 minus 2 times 4, it gives me minus 4. So here, if we look at the left hand side of this equation, so this bit and this bit, those are multiples of each other, but the right hand side is not. Since it's not the same multiple. So these are 3 times each other, but here these are not, which means these two lines are parallel, but they are not the same line. So if we then go and start looking at our diagram, what we actually have in effect here is this situation. So these two lines are parallel, but they are not like the same. So that's what's happening. So why is that working sometimes and working not the rest of the time? I don't know. These are both parallel. Essentially, there's no solutions to this. So this means they are not consistent. And there's no solutions. But importantly, none of these are multiples of each other, so they can't be parallel. Which means that it's going to be a sheaf or it's going to be a prism. But because this pair of equations that I make from eliminating x gives me a pair of inconsistent equations itself, that means that it must be a prism. It's quite a hard topic. Have a go at 6F and the mixed exercise now, and I've set you some homework on Google Teams too. So have a go at that, and then send me any messages if you have any questions. I hope you're enjoying. Well, I hope you're enjoying being at college. I'm very bored at home, so please keep me occupied. Okay. Thank you very much for watching. Goodbye.